Hello everyone. In this demonstration, we're going to show you how ChipNexus's FPGA agent handles an end-to-end design flow using a signal de-interleaving application as our showcase. We start by feeding NEX our design specifications for a dual-signal LVDS de-interleaver. This is a multi-clock domain design requiring a 100 MHz internal clock to process a 20 MHz serial stream. For our board, we specify an RTX 7 platform that prioritizes I/O accessibility to facilitate real-time observation with a logic analyzer. NEX utilizes its advanced tool use capabilities to directly interface with Vivado. It autonomously queries board availability and cross-references features against our technical constraints. NEX then moves to creating the project environment. It performs the necessary actions on the file system to structure our workspace, always asking for explicit permission from the user before executing any file operations, and makes direct calls into the Vivado environment. NEX analyzes the design specifications to determine which components benefit from vendor-provided IPs versus custom generation. It identifies available IPs within Vivado and handles the instantiation, in this instance, automatically selecting and configuring the Clocking Wizard IP to manage our system clock requirements. What sets NEX apart is its self-awareness and ability to adjust to errors. In this case, NEX initially provided detailed clock configuration data that was incompatible with the specific vendor IP version. Recognizing the conflict, NEX autonomously pivots, abstracting the requirement to higher-level information that Vivado can directly consume to successfully configure the clocking core. With the infrastructure in place, NEX moves to the core implementation. It translates our high-level specifications into synthesizable RTL, intelligently defining module boundaries and port mappings for the de-interleaver. NEX handles the file system creation for these source files, ensuring the directory structure is optimized for the Vivado project hierarchy. The tool then assembles the complete system by generating a top-level RTL wrapper. This wrapper serves as the structural glue, interconnecting our generated modules with the instantiated IPs and defining all top-level I/O signals. Simultaneously, NEX generates the necessary Vivado TCL scripts to programmatically add these sources and set the top-level reference at the project level. NEX handles the automated generation of XDC design constraints. It translates high-level requirements into precise Vivado syntax, defining everything from primary system clocks to physical I/O mappings. In this specific de-interleaver design, NEX identifies the asynchronous boundary between the clock domains and applies false paths and timing exceptions. With the project fully staged, NEX leverages its robust tool use capabilities to directly trigger and control the Vivado synthesis and implementation engines. It manages the entire synthesis and place and route process programmatically, ensuring the design transitions seamlessly from RTL to bitstream. Once the implementation is complete, NEX automatically pulls the various implementation reports back from Vivado for a detailed audit. It doesn't just aggregate timing and resource utilization data into a single report. It actively reviews all warnings and errors. NEX provides a prioritized list of critical warnings and offers specific improvement suggestions to further optimize the design. In just a few prompts, we've transitioned from a high-level specification to an implementation-ready FPGA design. NEX hasn't just automated the clicks, it has acted as an expert FPGA engineer, managing complexity and self-correcting at every stage. This is the future of hardware development. Faster, smarter, and end-to-end. Thanks for watching.